Imagine you're inside a giant bubble. Everything you've ever known, every planet, every moon, every asteroid, exists inside this bubble. The bubble has a wall, and for decades, scientists assumed that wall was solid, a clean, sealed boundary separating us from the rest of the universe. Voyager 1 just proved that wall has a crack in it. Not a metaphorical crack, an actual measurable leak, where particles from inside our solar system are bleeding out into interstellar space, and where energy from the universe outside is seeping in. And now, after nearly 50 years of travel across 24 billion kilometers of space, this tiny spacecraft, running on less power than a refrigerator light bulb, has handed scientists evidence that rewrites what we thought we knew about the very edge of our cosmic home. This story has everything. A 47-year-old spacecraft still sending data from beyond the solar system, a boundary that behaves nothing like textbooks described, and a discovery that changes how we think about Earth's protection from deep space radiation. Stay with me, because this one genuinely matters. Welcome back. Or if you're new here, welcome. This channel covers the biggest stories in space, technology, and our planet's future. And today, we're talking about one of the greatest engineering achievements in human history, the Voyager program. Here's the quick version for anyone who needs it. NASA launched Voyager 1 in September 1977, the same year Star Wars came out, for context. Its original mission was to fly past Jupiter and Saturn, snap some pictures, and collect data. That mission was completed by 1980. But instead of switching the spacecraft off, NASA kept it going, and going, and going. Today, Voyager 1 is the most distant human-made object ever built. As of mid-2025, it sits roughly 196 to 167 astronomical units from Earth. That's more than 24 billion kilometers. And it's still moving, still transmitting, still doing science. A one-way radio signal from Voyager to produce now takes approximately 23 hours to reach us, nearly a full day, just for light-speed communication. But here's what makes the latest findings so significant. Voyager 1 didn't just go far. It crossed a boundary that no spacecraft had ever crossed before, and in doing so, it exposed something about that boundary that nobody expected. To understand what Voyager found, you first need to understand the Heliosphere, the giant protective bubble I mentioned at the start. Our sun is constantly releasing a stream of charged particles called the solar wind. This wind flows outward in every direction at roughly 400 to 800 kilometers per second, carrying the sun's magnetic field with it. As it travels, it pushes outward against the gas and plasma that fill the space between stars, what scientists call the interstellar medium. Eventually, that outward push runs out of energy. The solar wind slows, stalls, and is finally overpowered by the pressure of interstellar space. The boundary where this happens, where the sun's influence finally gives way to the universe beyond, is called the Heliopause. Think of it as the edge of our solar system, not where the planets end. Pluto is well inside the Heliosphere, but where the sun's reach truly stops. Inside the Heliosphere, we are partially shielded from galactic cosmic rays, high-energy particles produced by supernovae and other violent events scattered across the galaxy. Without this bubble, those cosmic rays would bombard Earth and the planets far more intensely than they do now. The Heliosphere isn't just a scientific curiosity, it's part of what makes life on Earth possible. For decades, scientists modeled this bubble as a clean, sealed structure with a relatively sharp outer boundary. Voyager 1 crossed that boundary on 25th of August 2012, becoming the first spacecraft in history to enter interstellar space. And what it found there started to unravel the tidy picture almost immediately. When Voyager 1 crossed the Heliopause in 2012, scientists expected a dramatic shift. Inside, solar particles, the sun's magnetic field, relatively low levels of cosmic rays. Outside, a completely different environment dominated by interstellar plasma, a different magnetic field direction, and a flood of galactic cosmic rays. First, the magnetic field. Scientists expected the direction of the magnetic field to change significantly as Voyager crossed the Heliopause. Inside the heliosphere, it aligns with the sun's field. Outside, in interstellar space, it should follow the local galactic field, pointing in a different direction. But both Voyager 1 and later Voyager 2, which crossed the Heliopause in November 2018, found that the magnetic field direction barely changed at all across the boundary. That result, confirmed twice from two different crossing points, challenged the fundamental models physicists had built for how the heliosphere interacts with interstellar space. Second, the leak. Scientists originally assumed that solar particles would be fully contained within the heliosphere. Voyager 1 saw no leakage at its crossing point, but when Voyager 2 crossed at a slightly different location 6 years later, it detected a small but measurable trickle of solar particles, streaming through the heliopause and out into interstellar space. The boundary, in other words, was not sealed. It was permeable. Solar particles were leaking out, and that means, by the same logic, that interstellar particles can seep in. Research published in early 2024 deepened this picture further. Instead of a thin, sharp boundary line, on the kind textbooks had long described, the new data from both Voyager spacecraft suggests the Heliopause is more accurately described as a thick, layered boundary region. Not a wall, a transition zone. And within that zone, the magnetic field lines from inside and outside the heliosphere appear to connect, which is likely why particles can cross in both directions in the first place. There is another discovery from this boundary region that, when you hear it described, sounds genuinely impossible. As the Voyager spacecraft passed through the Heliopause, they recorded temperatures in the surrounding plasma. Those temperatures were extraordinary, somewhere between 30,000 and 50,000 Kelvin, far hotter than the surface of the Sun, which sits at about 5,678 Kelvin. This scorching region at the very edge of the solar system has been nicknamed the Wall of Fire. And the immediate question is obvious. How is Voyager still intact? First, the magnetic field. Scientists expected the direction of the magnetic field to change significantly as Voyager crossed the Heliopause. Inside the heliosphere, it aligns with the Sun's field. Outside, in interstellar space, it should follow the local galactic field, pointing in a different direction. But both Voyager 1 and later Voyager 2, which crossed the Heliopause in November 2018, found that the magnetic field direction barely changed at all across the boundary. That result, confirmed twice from two different crossing points, challenged the fundamental models physicists had built for how the heliosphere interacts with interstellar space. Second, the leak. Scientists originally assumed that solar particles would be fully contained within the heliosphere. Voyager 1 saw no leakage at its crossing point. But when Voyager 2 crossed at a slightly different location 6 years later, it detected a small but trickle of solar particles streaming through the Heliopause and out into interstellar space. The boundary, in other words, was not sealed. It was permeable. Solar particles were leaking out, and that means, by the same logic, that interstellar particles can seep in. Research published in early 2024 deepened this picture further. Instead of a thin, sharp boundary line, the kind textbooks had long described, the new data from both Voyager spacecraft suggests the Heliopause is more accurately described as a thick, layered boundary region, not a wall, a transition zone. And within that zone, the magnetic field lines from inside and outside the heliosphere appear to connect, which is likely why particles can cross in both directions in the first place. There is another discovery from this boundary region that, when you hear it described, sounds genuinely impossible. As the Voyager spacecraft passed through the Heliopause, they recorded temperatures in the surrounding plasma. Those temperatures were extraordinary, somewhere between 30,000 and 50,000 Kelvin, far hotter than the surface of the Sun, which sits at about 5,178 Kelvin. This scorching region at the very edge of the solar system has been nicknamed the Wall of Fire. And the immediate question is obvious. How is Voyager still intact? The answer lies in density. Temperature in a gas or plasma measures how fast individual particles are moving. But if there are almost no particles present, there is almost no heat to transfer. The plasma at the Heliopause is so incredibly thin, so close to a perfect vacuum, that even at those extreme temperatures, Voyager encounters essentially no thermal energy. It is like being in an oven where the air has been almost entirely removed. The thermometer reads boiling, but you feel nothing. Still, this discovery shattered expectations. Nobody had predicted a region this hot at the boundary of the heliosphere. Understanding why it's there and exactly how it relates to the leakage and the unusual magnetic field behavior is now one of the central questions driving heliospheric science. You might be wondering, this is all fascinating, but does any of it matter for life here on Earth? The short answer is yes, and here's why. The heliosphere's integrity directly affects how much galactic cosmic radiation reaches the inner solar system, including Earth. High-energy cosmic rays have been linked to a range of effects. They can damage electronics and satellites. They pose radiation risks to astronauts on long-duration missions and over geological timescales. Some researchers believe fluctuations in cosmic ray levels may even have influenced biological evolution on Earth. If the Heliopause is not the solid shield we once believed, but instead a permeable layered boundary with cracks that let particles through, then our picture of how protected we actually are needs to be revised. It also changes how we plan for deep space. Missions, particularly crewed missions to Mars or beyond, where astronauts will spend months outside Earth's magnetic field and partly reliant on the heliosphere for protection. There's also a broader scientific implication. The heliosphere is, in a sense, our local example of a stellar bubble, and stars across the galaxy produce similar structures around themselves. By finally understanding the real shape, structure, and permeability of our own heliosphere, scientists can build better models for how all stellar systems interact with the interstellar medium. Voyager's data isn't just about our solar system, it's a template for understanding stellar physics everywhere. To follow up on Voyager's findings with better resolution, NASA launched the Interstellar Mapping and Acceleration Probe, IMAP, in 2025. Described by scientists as IBEX on steroids, IMAP is designed to remotely sense the Heliopause boundary and map it in far greater detail than ever before, building directly on what Voyager 1 and 2 revealed. It is worth pausing here to appreciate just what an achievement Voyager 1 itself represents. Launched in 1977, it carries computing power roughly equivalent to a pocket calculator by today's standards. It runs on a nuclear power source, a radioisotope thermoelectric generator, that loses about 4 watts of power per year. To conserve energy, NASA has been methodically shutting down instruments. In April 2025, engineers at JPL powered down one more instrument to extend Voyager's operational life as long as possible. Despite all of that, Voyager 1 is still transmitting, still doing science, still sending back data from a region of space no other human-made object has ever reached. At its current distance, the signal takes 23 hours to arrive, meaning every command sent from Earth gets a response nearly 2 days later. Engineers at JPL manage this spacecraft across 24 billion kilometers with the kind of patience and precision that is genuinely difficult to comprehend. At some point in the coming years, possibly before the end of this decade, Voyager 1 will go silent. Its power will finally run out. When it does, it will still be traveling outward at roughly 17 kilometers per second, and it will continue doing so in silence for millions of years. Here is my honest take on all of this. The idea of a crack in our solar system sounds alarming, and the headline is designed to make you feel that way. But what this actually represents is something far more interesting than danger. It's the discovery that our protective bubble is more complex, more dynamic, and more connected to the wider galaxy than we ever gave it credit for. The heliopause isn't a sealed wall, it's a breathing, permeable boundary, a place where the sun and the galaxy are in constant, turbulent conversation. Solar particles leak out, interstellar particles seep in, the magnetic field connects across the boundary in ways we didn't predict. And none of this was known before a 47-year-old spacecraft, built with 1970s technology, crossed that boundary and told us so. That, to me, is not disturbing. That is extraordinary. Voyager 1 has done more to reshape our understanding of the solar system's edge than any other instrument in history. And it still isn't done. So here's the question I want to leave you with. If the heliopause isn't the sealed barrier we thought it was, what else about our solar system's structure might be wrong? Drop your theory in the comments. I genuinely read them, and the best ones always spark the best conversations. If this video gave you a new perspective on where our solar system ends and the universe begins, hit that like button. It helps the channel keep exploring stories like this one. And subscribe if you want to be here for the next time Voyager, or something we haven't even launched yet, changes everything we thought we knew.